So we left off yesterday pretty close to the end of 6.4. We had gone through the table and how you describe all the original asymptotes for each of the four trig functions, and then how you describe the new ones. But we only got through ones yesterday that didn't have any transformations. So it had a 1 in front of the x and another 1 in front of the x. The next one we were going to do has a transformation like the one in the homework. So let's try this one. And they're not asking for the domain and the range here. We've done that, but they don't want it on this one. They just want to know the period and the asymptotes. So remember, the formula for period depends on whether you're using, well, it depends on what trig function you're using. It's either pi over b or 2 pi over b. What's the formula for the period when you're doing cosecant? Yep.
2 pi over b.
Yep. So it's 2 pi over. And what's the b in this case? Yeah?
3, right?
3. Yep. Okay, so there's part of the question. There's your period. That's what you need to put on the end of your answer, plus the period times n. Because whatever asymptote we find, it's going to keep repeating. How often does it repeat? Every cycle. You're going to get another asymptote. All right, so now we need to find the asymptotes. Okay, step 1. Find the original asymptotes and then set them equal to the argument. So that's kind of combining steps 1 and 2 together. Find the originals, set them equal to the argument. All right, so we are dealing with cosecant. What are my original asymptotes for cosecant? Yep.
0 and pi.
0 and pi, and I'm going to set them equal to the what? Yep.
Argument.
Yep. We're going to set the 0 and the pi equal to the argument to figure out how this 3 is changing things. So that's the original. That's the original. Set them equal to the argument. What's the argument in cosine 3x? Yep.
3x.
3x. Yep. It's the entire thing if you imagine parentheses like this. Well, there's usually no decimal point like that. 3x. Now, when you put a 3 here, this is a horizontal stretch or compression. Whenever you have a 0 and you stretch it or compress it, 0 always stays a 0. When you divide each side by 3 to solve this, nothing happens to that first asymptote. Okay, so that's our first one. I'm going to write it the way we normally do with the variable on the left. Leave a little bit of room on the end because you need to put plus the period times n. Because that asymptote repeats. Okay, now let's solve this one. How would I get x by itself in the second one? Yeah?
Divide by 3.
Divide by 3. And that asymptote that was originally at pi has now been squished by 3 times as much. So it's not at pi anymore. It's at pi over 3. So those are what happened to the 2 original asymptotes in the table. 0 stayed at 0, and pi got squished to pi over 3. Now, each of these asymptotes is going to repeat regularly. So we need to put the last thing I told you. The answer that you just got plus the period times n. Okay, what's the period of the one that we just did? Lauren?
2 pi over 3.
Right. So this first asymptote is going to occur at 0 plus every multiple of 2 pi over 3. The second asymptote is going to occur at starting at pi over 3, and then adding multiples of the period from there. And that's exactly like the one in the homework. If you don't put the 0 here, that's okay, because you don't need to put 0 when you do addition. If you leave it like that, that's also okay. But that's how you find your two asymptotes. Okay. Any question on how we did that? Mm-hmm.
This is kind of a random question, but would to like indicate a horizontal asymptote, would that equation be negative?
Horizontal asymptotes, which we are not talking about at all in this, are y equals instead of x equals. But yeah, you do not have to worry anything about horizontals in this stuff. Just verticals.
Wait, so if we'll always do that if there's a number before the x, right?
Yeah, if there's a number before the x, then if I go back to the table, where is it? If there's a number before the x, then these original asymptotes are not going to stay where they are. If they're going to shift. The only one that would stay where it is if it's at 0, because that one doesn't move. But everything else is going to shift. Yeah. Any other questions on that one? Yeah.
Last time I was doing the homework, I was getting confused why I didn't find like a break or a horizontal asymptote in the cotangent function. There should be one, I just didn't get one.
Maybe you weren't zoomed out far enough to see it.
Oh, yeah, that's probably it.
Could be it. So let's actually do that here. It says to graph it and show 2 cycles. Well, 1 cycle is 2 pi over 3. So how much is 2 cycles? Yep.
4 pi over 3.
4 pi over 3. So if you want to show 2 cycles on the screen, the easiest way to do it, well, you've got to set a window that's 4 pi over 3 wide. I think the easiest way is to just go 0 to 4 pi over 3. Okay, that's what I do. So let's put in 4 pi over 3. Okay, so put that in. And now put your function in y1. Which function do we flip to put in cosecant? Because I don't have a cosecant button. Yeah? The sine. So we have to do 1 divided by sine, but not just sine of x. 3x. Okay, we have to keep that 3 there. Right, and we're looking at 2 cycles. Remember, a cycle for cosecant is a U shape and an N shape. So you should be seeing 2 U shapes and 2 N shapes. We may cut one in half. No, we didn't this time, but if you did, that would have been okay. So there's your first U and N shape. There's your second U and your second N. You're looking at 2 cycles right there. Yeah.
What did you put for the line in there?
I think I left it -4 to 4. Yeah. It doesn't really matter because it goes up and down forever. I mean, I wouldn't set it to like, I wouldn't do something like -400 to 400. That's probably not going to look good now because you've stretched it so much. They're probably going to look like, you know, if you even see them as U shapes and N shapes, they're going to look very skinny. Let's see. Oh no. Yeah, no. They're so skinny you can't even see them. So there's your U shape, N shape. Well, I don't know. Yeah, don't set it that high. Yeah, it doesn't look good. Yep.
You're getting like the window for, or like when you're trying to get the length for the window, are you just multiplying the numerator or whatever it wants for you to get?
The width of it, yeah, I'm multiplying the 1 cycle length by how many cycles they want me to see. So if they wanted to see 5 cycles of U shapes and N shapes, I would multiply this by 5 and say 10 pi over 3. Yep. All right, so let's take a look at the last thing, which is graphing on the calculator. So keep in mind what happens when you graph a trig equation. You could end up with something like this. Here's a simple sine wave. And let's put a horizontal line. It's a little further. Now we have a horizontal line. If you could zoom out forever, how many times would the horizontal line and the wave cross each other? Yeah. Right, it would be infinitely many. If you focus on one cycle, that's from here to there. In that red box is exactly one cycle. How many times do the wave and the line cross in one cycle? Yeah? Twice. So this kind of problem has 2 answers per cycle. This answer and this answer are really the same answer. And then this answer and that answer are also the same answer. How much later is the red answer going to repeat itself? In general, it's going to repeat every cycle, whatever a cycle is. If it's 2 pi, pi, right, whatever. But this red answer is going to repeat itself every cycle, and then so is this green answer. So when we want to find all solutions to a trig equation, what we're going to do is we're going to graph it, and we're going to find all the answers in one cycle first. Then to indicate that those answers repeat, we're going to do what we always do. We're going to put plus a period times n. All right, so if you can find one solution in a cycle, then that really means there's infinitely many, because you could zoom out and keep finding that solution later cycles. Well, if there's infinitely many, we can't write them all down. So the way we do it is you write one of them, and then this part on the end tells me that that answer repeats. Remember, n here is an integer. N is the number of cycles later that you want to find the next answer. And you have to write this down for as many answers as you have. So in the last problem, we had 2 cycles per answer. So you're going to have to write something like this twice. If you had 7 answers in a cycle, then you need to write 7 of these down. Usually we're going to have 2, maybe 3. That would be typical. All right, so we'll try a couple of these where basically we're just finding an intercept. That's how you're going to get the b value. And the period, you're going to use the formula pi over b, or 2 pi over b. Depends on what trig function you have. It's very important you set your window to 1 cycle. If you set your window bigger than 1 cycle, you're going to confuse yourself with how many answers you really need to write down. So set it to 1 cycle. Okay, so find all solutions to cosecant x equals negative 1.6. All right, so let's put cosecant in on y1, and then we'll put negative 1.6 on y2. All right, cosecant, don't have a button for that one. Okay, how do we put in cosecant? Okay.
You put 1 over the negative 1.6x. 1 over sine.
1 over sine. So what's on the left is y1. What's on the right, I put in y2. Point is, you're going to put something on one side in y1 and put the thing that's on the other side in y2. Okay. Now, what did I say to set the window to? Like, you want the width of your window to be how big for every problem? Yeah?
The length of one period.
The length of one period. Yeah, so we need to find that. Didn't say to find the period, but you're not going to be able to answer this question without doing it. So you need the period. Okay, what's the formula for the period of cosecant? Yep.
2 pi over b.
2 pi over b. And in this case, what number is in front of x?
1.
1. So there is no transformation. So whatever answer we find, we need to put plus 2 pi n on the end. And that tells me how wide to set my window. Set your window so it's exactly 2 pi units wide. What's the easiest way to create an x min and an x max that have a difference of 2 pi? There's infinitely many ways, but I think one way is the easiest. Yep.
You set your x min to 0 and x max to 2 pi.
Yeah, just go 0 to 2 pi. That's the easiest way to do it. Okay, high and low, -5 to 5, that's fine because we're not doing any kind of stretching here, so we don't need to worry about anything like that. Okay, so you're going to see one U shape and one N shape if you set this to one cycle. So that looks good. Okay, how many answers does it look like we get?
2.
Yep, 2 answers per cycle. I don't know what they are yet, but I do know what each one of them is going to have on the end of it. What are we going to put on the end of each answer? Yep.
2 pi n.
Plus 2 pi n. Yep. Okay. How am I going to get these 2 answers? We've done this before on the calculator. Yep.
Second calc intersect.
Yep. Can I just do second calc intersect? It does matter where you put your guess because you want to make sure you get the one on the left, and then the one on the right. So 3.82. And that answer is going to repeat itself every 2 pi units. And the other answer? Just move your cursor a little bit closer to the right. That should be good enough. 5.61. And that's how you describe all solutions, by putting the plus 2 pi in. Okay. Question on it? Yeah.
And that's the equation for solution, not asymptote, right?
Oh yes, these are solutions. These are not asymptotes at all. Don't put into anything with asymptotes.
And then my other question for that, what was the equation as you typed it into the calculator?
So that is what I put into the calculator. That was a 1. Okay, let's try, we'll finish up this part with this. Tangent x equals 2.5. Well, this time I have a button for that, so all I have to do is press the button. Tangent x. Don't clear it once you type it in. It's not what you want to do. What am I going to put on y2 this time? Oh, Lucas?
2.5.
Yep. We'll put in 2.5. Now we need to set our window to 1 cycle. What's the cycle length for tangent? What's the formula to find the cycle length? Yep.
Pi over b.
Pi over b. And in this case, b again is a 1. So I'm going to set my window from 0 to pi. And remember what tangent looks like. It looks kind of like this. If you set your window correctly, you should see exactly one of those curves on the screen. If you see more than one, you didn't set your window right. All right, we're going to see one curve. It's going to be broken in half, but that's perfectly fine. It's just broken into two pieces because of the way I set the window. Hey, how many answers per cycle here? Yep, just one. Second calc intersect. It does matter where you put your cursor. You have to put it on the part of the graph that's the upper left part. If you put it on the lower right part, I don't think it'll find the intersect. 1.19. And I put this symbol because it's about what the answer is. It's not exactly what the answer is. So 1.19, that represents the first answer. And what do I put on the end of it to represent every other answer in this problem, left and right forever? Yep.
Plus pi over 1.
Yep, you can just put plus pi n since it's just over 1. That's fine. Any questions on that? Okay. All right, so last night we already did up to 20. 28. 29. Let's get that one. And Right, so that's going to be the first part of the homework, just those 4 questions. Page 352, 28, 29, 31, and 46. 46, you're finding all solutions. So you're doing what we just did on the board, plus 2 pi n. 29 and 31, you're only finding solutions in a certain interval. They tell you in the book, find all answers between, say, -3 and 3. That means you set your window to -3 and 3, and you just find what's on the screen. You do not put plus 2 pi n if they only want you to find answers in a certain section. It's like they're limiting the answers they want you to write for whatever reason. And then 28, that's one like we did last night. Find the domain, the range, the period, and the asymptote. That's kind of a review one. Okay. Any questions on that? Those 4. Okay. Okay, so the last section we're going to look at is 6.5. And we're going to split this section into 2 days. If it goes into Thursday a little bit, that's fine. It's Thursday again. That's a review day, so we don't have to rush to get through it. So what we're going to look at in section 6.5, kind of the big idea here is eventually I'm going to be giving you a triangle, and I'm going to label some pieces of information in it. Maybe I'll tell you this side is 4, and this angle is 25 degrees. And I'll ask you to figure out everything else in that triangle. That's the goal of this section. Find the other angles, find the missing sides. So that's what we'll talk about how to do. The kind of triangles that we're going to be working with in this section are specifically right triangles. Like the one I drew in blue. What does that mean? If a triangle is a right triangle. Because not every triangle is a right triangle. Yeah?
Right triangle has
one angle that's equal to 90 degrees.
Right, it has exactly one angle that is equal to 90 degrees. Here's a triangle without a 90. That is not a right triangle. Yep, that's an obtuse triangle. Or think of an equilateral triangle. That's acute. All the angles there are less than 90. They're all 60. Okay, this is the type that we're working with. Okay, a few different terms come up in a right triangle that we use to describe some things. What do we call the side that's the longest side and it's across from the right angle? There's a name for that side. Yeah? Yep, that's called the hypotenuse. And does anybody remember what we call the other two shorter sides? The long side is the hypotenuse, yep? Yes, the legs. Now, when we label sides in a triangle that we don't know, we use a variable. Just like anything else we don't know in algebra, we use a variable. And the variables that we use most of the time in a right triangle are A and B for the two legs, and we use C for the hypotenuse. You don't have to use those letters, but most people do. And there's a certain theorem based on a right triangle that uses those letters. Does anybody know what theorem I'm thinking of?
Pythagorean.
Yep, we're going to talk about the Pythagorean theorem in just a second. So here's a diagram of a right triangle with everything labeled. This angle, and actually I could do this one too. That angle are both acute angles. Because what do all the angles in a triangle add up to?
180.
They add up to 180. And if you're dealing with a right triangle, you've already used up 90. So what does that leave left for the other two? It leaves 90 for the two of them, but it has to be split up. So each one of these angles is always less than 90. Okay. So the Pythagorean theorem. This is a theorem about the side of the triangle. It has nothing to do with the angles in a triangle. It's all about sides. Does anybody know what is the Pythagorean theorem? Yeah? Okay, now what does that mean? Can you explain to me what's the A, the B, and the C? Specifically. Because you could say the Pythagorean theorem is q squared plus r squared equals s squared. As long as you correctly tell me what the q, the r, and the s. Yep.
The length of the two legs added together squared equals the length of the hypotenuse squared.
Yeah, that's the idea of the theorem. If you take the length of each leg, square them and add them together, that's equal to the length of the hypotenuse squared. If that formula doesn't work in your triangle, one of two things. You did the formula wrong. Or you're dealing with a triangle that's not a right triangle. Okay, but that always has to work in a right triangle. Okay. Any question on that? So we've looked at the 6 trig functions before when we did unit circle trig. We had sine, cosine, tangent, cosecant, secant, cotangent. And the way we did them when we did unit circle trig was all based around finding a coordinate. We're not going to base it around finding a coordinate. We're going to base it this time around the lengths of sides in a triangle. Unit circle trig and what we're doing here are the same thing. We're basically just using different names, but it's exactly the same thing. So each trig function that we're going to look at is a fraction of 2 sides in the triangle. There are three different sides to pick from. Opposite, adjacent, and hypotenuse are the names that we're going to use. I'll explain what opposite and adjacent mean. Let me give you the definitions first, and then I'll explain. So the way we're going to define the sine function in this section is to take the length of the opposite side and divide by the length of the hypotenuse. The way we're going to define cosine is to take the length of the side that is adjacent and divide by the length of the hypotenuse. And the definition of tangent is the length of the opposite divided by the length of the adjacent. So in each of these fractions, we're dividing two numbers that represent lengths. Can somebody give me a length? Give me any length you want. Just give me a length. 2 what? Meters. Okay, somebody give me a different length, but I need it in meters. So give me any length you want. Yeah? 7. When you take 2 meters and divide by 7 meters, something there cancels out. What would cancel out? Because it's in the top and the bottom. Yeah? Meters is gone. So what that means is when we do a trig function, when we write an answer, it does not have a label. The label, whatever the lengths were, is gone. So the answer to like sine of an angle is just 2/7. 2/7 what? Nothing. Just 2/7. It has no label. No radians, no degrees, no meters. Just the number 2/7. So in this kind of stuff, you don't have to worry about putting labels on anything because the label cancels. And sometimes people use, forget what it's called, an acronym, a way to remember these 3 trig functions. Does anybody remember something or know something they've learned before to help you remember those 3? Yeah? Yeah, you remember this, Sakatoa. It tells you which trig function is which. So the S stands for sine, and the H is opposite. The O is opposite, and the H is hypotenuse. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent, TOA, toe. Tangent is opposite over adjacent. So if you break it up into those 3 pieces, it tells you each of those 3 fractions. Sakatoa. One year I asked for that, like how do you remember the trig functions? And somebody said Sacagawea. Sacagawea is not going to help you. She may help with something else in history, but she's not going to help you remember your trig functions. So Sakatoa, not Sacagawea. All right, so we've got the first 3, and then the next 3 are the cosecant, secant, and the cotangent. And what's the connection between the ones on the right and the ones on the left? We use this connection all the time when we type them into the calculator. Yeah?
The ones on the right are inverse or reciprocal?
Reciprocal. Yes, they have reciprocals. So based on the fact that sine and cosecant are reciprocals, what do you think the formula for cosecant is going to be? Yeah?
Hypotenuse over opposite.
Hypotenuse over opposite. Yep. I just abbreviated. What about the formula for secant? Yeah, Caleb.
Hypotenuse over adjacent.
That's going to be hypotenuse over adjacent. And what about the formula for cotangent? Yeah.
Adjacent over opposite.
Say it one more time.
Adjacent over opposite.
Yep, adjacent over opposite. Good. Now, to remember those, I don't remember them directly. I just remember the three on the left, and then I remember, okay, the other ones are just what you get when you flip them. Because if you try to make up a word with these, like those, it doesn't work quite as nice. You get CHL, SAH, CAO. You get Choshikawa. I don't think many people remember Choshikawa. I think they just use Sakatoa. I guess if you want to go with Choshikawa, then have fun. Oh, maybe Google Choshikawa. Maybe somebody else came up with that. So hypotenuse, that's the easy one, right? The hypotenuse is always the side that's across from the 90. But the opposite and the adjacent don't have a fixed place. Opposite and adjacent are what we call relative. It's kind of like, for me, if I said left and right. My left is towards the door, my right is towards the windows. That's because left and right is relative to which way I'm facing. Your left and right are the opposite of what I just said. So when we talk about opposite and adjacent, we have to understand that it's opposite and adjacent from a certain spot. And that's what I'm going to show you right now. So let's draw a triangle. And the spot that the perspective in the problem is going to be from, they're going to mark it with an angle. So if I mark my angle in the lower right, pretend like you're standing right there and you're looking out at the triangle. Opposite is the side that's furthest away. Adjacent is the side that's right next to your angle. And if you're thinking, well, wait, you got two sides next to the angle. Yes, but one of them already has a name. It's hypotenuse. It doesn't matter how you flip or rotate that triangle. It all depends on where you put theta. If you put theta at the top, what side would be opposite theta now? Yeah?
The bottom side.
The bottom side. I can't say the bottom side is always opposite, but it's opposite in this case. Just like for the direction I'm facing, left is the door. If I face a different way, the door is no longer left for me because I'm facing a different way. So theta makes that opposite, makes that side adjacent, and the hypotenuse is the side that's always across from the 90. So hypotenuse, is like, if I use my analogy in this room, would be like up. Doesn't matter which way you face. Up is the same for everyone. Okay? Doesn't matter where you put theta. Hypotenuse is always the same. It's across from the 90. Question on that? So what I want to look at now is, let's say we had a trig function, right? And I said to you, for example, I want to find the sine of 30 degrees. The question I want to look at is, does it make a difference if you find the sine of 30 degrees in that small triangle? Or you make a copy of it and you proportionally enlarge it. That's proportional. I didn't like stretch it out or anything. It's like I put it on a photocopier and just hit enlarge. So I kept it proportional. If I find the sine of 30 in the small triangle or the big triangle, do you think the answer is going to come out the same or different?
The same.
It's going to come out the same. The size of the triangle has nothing to do with the trig function, whether it's a small or a large version. Okay. Does anybody remember what you call these two kinds of triangles? They're not congruent, because congruent means they're identical. But one is an enlargement of the other, and there's a name for that. Yeah?
Is it similar?
These are called similar triangles. Similar triangles mean all the angles are exactly the same. So those are similar. So if you draw two right triangles and all the angles are the same, that is called similar. So what that means is that if you pick an angle and you pick a trig function, the trig function of an angle always has the same value for every angle that you pick. So like the sine of 30 degrees is always the sine of 30 degrees. It doesn't matter if it's in a small triangle or a big triangle. It's always the same. So here's an example of two similar triangles. And the one on the right is a scale factor of 2. It's double the size of the one on the left. But they are similar. They have the same angles. I want to pick a trig function in that triangle, and I want to find it in the small one, find it in the big one, and see if it comes out the same. Let's do the third. Okay, so don't worry about the sixth. Let's find the sine of 30 in the small triangle. What's the definition of sine? What two sides are we supposed to divide? Yeah?
Opposite over hypotenuse.
Yep. So in the small triangle, what side is opposite the 30? Yep. 1. And what's the hypotenuse in the small triangle? 2. So there's the sine of 30 in the small triangle. Now let's do it in the big triangle. So same thing. Everything is from the perspective of the 30 because I picked the 30. That's the only reason. What side is opposite 30 in the big triangle? Yep. 2. And sine is opposite over hypotenuse. What's the hypotenuse in the big triangle? Yeah.
4.
4. And what is 2/4 reduced to? 1/2. So the point is whether you find the sine of 30 in a small triangle or a gigantic triangle, the sine of 30 is always 0.5. It doesn't change. Any question on that?
So, if it's test says, will you give a test where you have to get the old data, or would you give us the data?
Most of the time, you're going to be given a theta, and you're going to have to figure it out.
Okay.
Yeah. I think I have one. I just want to see where I plan on stopping. We'll see if we get to that. All right, so how do you find all 6 trig functions? The sine, the cosine, all 6. If I give you one of them. Well, let's look at, don't write this down yet, but just look at the kind of problem we're going to do. Okay? I'm going to tell you that the sine of theta is 5/6. If I tell you that the sine is 5/6, what 2 things have I really given you? As long as you know what sine means. Max?
The opposite and hypotenuse.
I've told you the opposite and the hypotenuse. So draw a picture. Doesn't matter where you put theta. You could put it in the top. You could put it in the lower right. You're going to get the same answers when you go through. By telling you sine of theta equals 5/6, that's basically what I've told you. But the problem is, to do the other trig functions, you're going to need this side. How are you going to get the bottom side if you know the other two? Yep. Yep, we can use the Pythagorean theorem. So that's what I'm going to write down right now. So this is how you find 6 trig functions if you are given one of them. So take the trig function that I gave you. In the next problem, it's going to be sine, and use it to label 2 sides of a triangle. Maybe you'll know the opposite and hypotenuse. Maybe it'll be opposite and adjacent. But it'll be 2. Once you label those 2 sides, use the Pythagorean theorem to find the side that you don't know. Now you can figure out whatever you want once you know all the sides. So once you use Pythagorean theorem, you'll know every side. And you can determine any trig function you want. This is how you do it. Right there. Keep in mind, when we're doing a problem like this, you could get square roots. And if you get a square root, that is okay. We're going to leave it as a square root. Like if we get square root of 13, we're just going to leave that. We are not going to change it to a decimal. The only thing you do have to change is if you get a problem like square root of 20. We've talked before about how to reduce square roots. You do have to do that. What else do you have to make sure you do, or what else do you have to make sure that you don't do with square roots? You're not allowed to leave an answer happen if square roots are involved. Yep. You could have a negative square root. We're going to be talking about a lot of lengths here, so I think everything's going to be a positive number. But what can't you do with square roots in a final answer?
Can't leave them in the denominator.
You cannot leave them in the denominator. Okay, so that still applies. Just like it always does in algebra. Okay, so let's try this problem. So theta is an angle in a triangle. And we know that the sine of theta is 5/6. As we said before, they're telling me the opposite, and they're telling me the hypotenuse. Find all the other trig functions of theta. So this is what you have to do. All 6. Okay, so we don't know that third side, so you just could pick a letter to represent it for now. If you want to call it A or B, that's what most people would probably use if you're going to do Pythagorean. So let's call it A. Can somebody set up my Pythagorean theorem for me using the A, the 5, and the 6? Come on.
A squared plus 5 squared.
Okay, so A squared plus 25 equals 36. So what does a squared equal? 11. Well, we don't want a squared, we want a. So what do I do to get rid of the exponent of 2? Yep. Take the square root. And that's how we're going to leave the answer. Square root of 11. Okay, now let's use that diagram and write down all 6 trig functions. Right, what's my sign? Lauren?
Sine equals 5.
Yeah, that was so sine is 5 over 6. We could have done that one without doing the Pythagorean theorem. We could also do cosecant if we wanted right now. What's the cosecant going to be? Yeah.
6 over 5.
Yeah, we just flip it. So I might just do that one to get it out of the way because it's quick, simple, and it's done. All right, let's do cosine. What's my formula for cosine? Yep.
Adjacent over hypotenuse.
Adjacent over hypotenuse. And what's adjacent over hypotenuse in that triangle?
Square root of 11 over 6.
Okay, so there's my cosine. And what about tangent?
Maybe 5 over. Oh wait, which one?
Tangent.
5 over the square root of 11.
Okay, I'm going to put that over here, 5 over the square root of 11, because we need to fix it by multiplying top and bottom by square root of 11. So what do we get for final answer for tangent? Yep.
5 square root of 11. Oh yeah, over
Is it over 11?
It's over 11, because 11, square root of 11 times square root of 11 is 11. So it's still over 11. Now, it's not that this original answer was wrong. In fact, that's going to be important to do something else. It's just that it was written in a format you can't leave it that way, because it had the square root in the bottom. But keep that other answer in mind for when we do cotangent. Like, let's do cotangent right now. To do the cotangent, you have 2 things here. You have the original answer, 5 over square root of 11, and then you have the final answer. Which one of these would be better to flip to do the cotangent? They're the same. The 5 square root of 11 over 11, or the original? Max?
you flip the original.
Yeah. Why would you flip it?
Because it's just right, you don't have a square root in the bottom.
Yeah, when you flip the original, the square root goes to the top, you're done. If you flip the answer that we fixed, that's okay, but then the square root's going to go back to the bottom, you got to fix the whole thing again, and you're still going to get the same answer. All right, and my secant. The first step to find the secant is flip the cosine. But when we flip it, square root goes to the bottom. What would we get when we fix it? Right?
6 square root of 11 over 11.
Yep, 6 square root of 11 over 11. Good. Question on that? Let's see. All right, let's try one more. Let's do one more of those. Okay, so it says to find all 6 trig functions. And the angle we're doing is theta. Okay, and just to be clear about what we're finding here and what we found in the last problem, at no point in these problems did we ever find theta. We don't know how big the angle is. We know the sine of the angle, the cosine of the angle. We know a bunch of things about the angle. We don't know what the angle itself is. And that wasn't the goal of this problem. We were finding things about it, not how big it is. And same thing here. We're going to find out 6 different things about the angle. Any one of these 6 could be used to figure out how big is that angle. But again, that's not what we're doing. All right. So what would we do in that?
First, would we have to find the hypotenuse?
Yep.
By using the Pythagorean.
Yep. And this one comes out special. It's going to be 25 plus 144. The hypotenuse ends up being the square root of 169. Yeah?
13.
Which is 13. That is called a Pythagorean triple. Pythagorean triple is when you have a right triangle and none of the sides are decimals. 5, 12, 13 is one. 3, 4, and 5 is another. There's millions of them. But that's one. And the nice thing about a Pythagorean triple is you do not have to worry about any square roots. Okay. So let's start with my sine. Alexis, what's going to be the sine of theta? Yep, opposite over hypotenuse. Quinn, what's going to be the cosine?
That's gonna be 12 over 13.
Yep, 12 over 13. And Aiden, what's my tangent going to be? Yep, good. 5 over 12. And Brighton, what am I going to do with these 3 to get those 3? We're going to flip them. 13 fifths, 13 twelfths, 12 fifths. Okay. Any questions on that? Yeah.
So we get 13 just to the Pythagorean theorem.
Yep. Yep. It would come out to the square root of 169 in the Pythagorean theorem. Okay, so I'll put up that. I'm also going to put the other homework on the same page in case somebody goes to the end of the video, they see it. I'll need somebody to tell me what those 4 problems were in a second. Okay. 15, that's fine. Hold off on those 2. Definitely those 2. Okay, so that's what we'll do from the 6.5 part 1. And the other page, 352. Okay.
28, 29, 31, and 46.
31 and 46. Thank you.
You had annotated 31 with interval and 46 with all.
With all, yeah. And that's in the directions too, so that's fine. Okay, so that's homework for tonight. We'll finish up this part of 6.5 tomorrow. We'll start the next part, but we might have to finish it on Thursday. But you'll still have time to review Thursday.